Dear learners, our topic today is novel food processing technologies. So, in this session, we will study novel processing and the technologies which are used for novel processing of foods. If you look for the basic food processing technologies, which you have been taught already, that there is a processing conventional method which is temperature based. So that is called thermal processing of food. It gives preservation to the food. And otherwise, you would have also seen some other processes, low temperature applications, fermentation of the food products like curd. So that is, so means here the point is that basically food processing is aimed for preservation and also for preparation of the products. So there is a processing, there is preservation. And novel food processing are an alternate to the conventional processing in a way. So if you see the basic processing or the conventional processing technologies which are for the foods, there are two approaches: thermal, non-thermal. And in thermal, we have heating. That is, one is through steam, another through the dry heat, could be the dry air. Non-thermal could be the freezing, chilling, acidification or fermentation, ultrafiltration, and so on. While for the novel food processing, why the word novel is there? Novel processing is relatively newer techniques which are applied for the food processing, and they are alternative to the conventional processing. So there are two important points or the aspects which are just clarifying the meaning of the novel processing technologies. What do we include in novel processing technologies of food? Again, the same, non-thermal, thermal. There could be two approaches for it. First, I'll explain the non-thermal aspect. Non-thermal, what do we list in non-thermal? High pressure processing, pulse electric field, ultrasound, irradiation, ozonation, and so on. We'll take a detailed account of these non-thermal aspects, including I'll also cite few example of thermal. Thermal means what? Conventionally, we were heating through the steam or a flame heating or the hot air. But here, it's novel approaches are there which are in terms of using microwave, using radio frequency, ohmic heating, direct steam injection could also be there in the liquids. So they are the novel, unconventional, non-conventional kind of techniques which are applied for food processing. That's how they are novel. Now the question is that why we should have an alternate. We should look for novel. The novel main purpose is that once conventionally the food was processed using heat. So it gives both preservation and the cooking, so gives palatability. But along with the cooking, along with the efforts which we do with the high temperature for preservation, in addition to the preservation and the shelf life, there is a problem or there is also a challenge in terms of the deterioration of the physical, nutritional, sensory qualities of the food. So, if we look for example like protein is one of the heat sensitive nutrient, and it is denatured if exposed to the very high temperature. Denatured to the extent that it might not be available biologically to the consumer or the person who is consuming that food. Similarly, it may happen with vitamins. So, this is inevitable. Though we optimize or we put best effort in thermal processing so that these losses could be minimized. But in an attempt to further minimize this, the alternate was selected and scientists worked out for solutions, and they were named as the novel food processing technologies. So, as I mentioned, that alternatives of conventional processing, they are called novel processing technologies. And what are those technologies? Which we have already seen. Now, taking first out of these novel processing technologies, we are coming to high pressure processing. This is a novel approach, also non-thermal approach, and it can extend shelf life of food without affecting. When we say that without affecting sensory quality adversely, it means it is always a comparative statement. It has to be compared with the conventional processing technologies and mainly with thermal when there is a non-thermal approach. Here, what do we use? As name indicates, it is high pressure. So, pressure to what extent? The general range of the high pressure, which is defined or taken in different texts mention different ranges, but on an average, we can say that 50 megapascal and going up to the 1000 megapascal. But practically, commonly used or the typically food product applications, you would notice that 300 to 600 megapascal and the processing time can vary from 10 to 15 minutes or so. So this is what the meaning of the word high pressure processing means. You are applying pressure to the product. Product is pre-packed here, and this pressure which is exerted and experienced by the product, and that causes also the inactivation of microbes or the enzymes. If they are undesirable within the product, they can be inactivated. And the suitability of this particular technology is with the product which have the high moisture. So water content is high, compressibility of the water is good, they can be compressed and they can bear good pressure, and they can processed using pressure very well. I mentioned that this process is in container pasteurization kind of approach, where temperature is certainly not being used for killing microbes. Here we are changing that temperature or replacing temperature with pressure. So the packaging material is very, very important, that your package should be able to withstand to that high pressure. So what we need a package which maintains integrity, maintains barrier property during the processing, that high pressure to which it is being exposed. And packaging forms and the materials which can be used for it, they could be bottles, they could be pouches, cups, trays, and they are made of PET, PE, polyethylene, polypropylene, EVOH. And why these particular materials are selected? They are selected because they, even despite exposing to pressure, they maintain barrier properties, and moreover, the seal strength. When pressure is there, there could be opening of the seal. So they can withstand, the seal can also withstand, not only the material is withstanding, but the seal integrity is also there. Now, looking for that, where do we apply this particular technology or this particular process of high pressure? It is applied, I mentioned that it is giving a pasteurization kind of applications or the equivalence to the thermal processing. It can replace some of the thermal processes, for example, in juices, in jams, in jelly, in sauces, salad, puree, hummus kind of products. And in addition to this direct food applications where the products are being processed, they can also support in processing by enhancing the thawing and freezing of food. If somebody is interested in bioactive compound extraction, pressure treatments is also makes reach to the that whatever the solvent you are using or to the bioactive compounds, and so yield can be increased. Also, it is effective for the milk-based product, meat, poultry, and particularly like if there are seafoods, which is oyster or so, means they are disintegration from the cell, easy disintegration, and then their shelf life can be increased. So these are the basic applications for the high pressure processing. Now looking into that, how does it work? What are the principles which are behind it? There are two key principles which are taken into consideration when we deal with the high pressure processing. First principle is Le Chatelier principle. So what it says, that if there is a system is what? If you have a food which is packed, if you treat that as a system, so system is at a dynamic equilibrium. If it is disturbed, so means disturbed, how we are disturbing it? We are disturbing by applying the pressure. So if you are disturbing it, so it will shift to counteract the change in the conditions. Those conditions could be of any temperature, pressure, concentration of volume. So they'll counter the change. Here our major change is of pressure. So it means it will tend to the minimize that disturbance. It will ultimately will yield for a volume would be compressed or the decreased. So that is what the system will go to counter that change. Another important thing, if you can see here in this figure, this explains that how this principle is applied. You see that initially there is a piston which is and there are molecules which are available, they are distinct in color, and particularly A and B. If they are there and if you are compressing them will lead to a certain change. There could be the less number of molecule, there could be the size change in the molecule, some of the reactions it may lead to. So what do you see, that size which are indicating, so means the less number of molecule. A plus 2B is indicated as C plus D. So this is a change, volume reduction. How is it taking place? One thing is compressibility, but it is a dynamic equilibrium, so some of the reactions, interactions may also take place. The second principle is isostatic pressure. What does it mean? It means that the pressure is being transmitted. Say for example, if it is that piston and the system, we consider that whatever the volume inside, we put the pressure. Is the pressure uniformly distributed to all points within the system or not? So we want to have this process in such a way that it has to be uniformly distributed and instantly distributed. So this is what it says, that throughout the sample instantaneously and uniformly. It could be represented in this form. So you see that the package is there, though the pressure is there, but how does it stands within that high pressure? Pressure we have indicated it is 600 megapascal or more. So it withstands because net equilibrium is there. All side there are pressure is being applied. But under this pressure, under this compression, what happens? What we are targeting for, you see that there are two circles within that. It is indicated that how the cell behaves in it. So there is the cell membrane disruption, leakage of the intercellular material, and thereby the inactivation of cell take place. So the pressure which is accompanied by moderate uniform temperature, that is how does it happen? It is actually what is happening inside the system. A adiabatic heating is taking place. So that is due to the heat of compression. The pressure is being applied, so heat of compression is causing what? Causing the rise in the temperature. Though we call it a non-thermal, but there could be a significant rise depending on what pressure we are going to. So gradually we are increasing pressure. It also leads to the increase in temperature. Here, but that could not, the temperature will not go usually beyond 50. And there could be, if the temperature is increasing and product is able to withstand that temperature, there could be synergy of temperature and pressure also. Means both can together inactivate microbes better. However, keeping it non-thermal in interest of the product, sometimes cooling arrangement is also provided, though because temperature is increasing within the vessel. It along with the boundary, the heat transfer can be made and heat can be drawn away from the system. Now, moving to another method of novel processing technologies, that is pulse electric field processing. So it is the two words to see, that pulse and electric field. So we are applying electric field, that too is a very high intensity, usually 10 to 80 kilovolt per centimeter range, and in the manner of pulses. So pulse means on and off. And here in this process, sometimes a combination, their synergy is produced with that use of temperature also, which could be there 40 to 50. Otherwise, it can be at normal temperature or whatever the product temperature is. And in this high external electric field, what happens, that accumulation of charge will take place. So on where it will take place? It will take place along the membrane. And with that, you see that how the charge distribution is there when it is placed between electrodes. It means within the electrodes there is a high electric field. And for that, so there is a, particularly if you see that there is a drag on the surface. So that, what is it causing? Depending on that what value of electric field is there. So there is a critical electric field which is able to create pores within the cell of the microbes. They may be microbial cell, they may be plant cell, both. But we are targeting inactivation of microbes if we are targeting for preservation. So that's why I am calling it microbes. And depending on the value, means we are increasing E, that will, there would be a certain value which will initiate this pore creation or pore formation. And once it is sufficiently large, it will cause the irreversible damage to the cell. Cell will not repair thereafter, and that would be the inactivation of that particular cell through the kind of that potential which is developed due to the distribution of ions, that is called transmembrane potential. Now, where do we apply it? We apply in the, there are certain chambers which are designated as PEF chamber or pulse electric field chambers, or the locations where actually product is exposed to the high electric field. So there could be different design possibles. You see that there are 3 different designs: circular, where concentric electrodes are being used, yellow and black, that there are 2 different things. So means you have a insulating thing, you have, other than insulator, a material which are used for the forming of 2 electrodes. So within the electrodes you have to place the material or the food to flow. So there could be different designs which are possible. A tubular design could be there. There could be a flow which could be a channel kind of flow. That's how the parallel plates are shown, the yellow and the red one. So this is, and the electrodes are made of the material which is like titanium. And here, important to see that the kind of gap which is there between the electrodes, because electric field strength, you might recall that electric field strength would be affected not only by the whatever the voltage you are applying or the voltage across the food material, but also the distance between the electrodes. So means more D is more, which is in denominator, it will reduce the electric field. So that opening is kept not much higher. So that's also a limitation that of this particular method. You cannot have very high flow and throughput through the particular chamber. Now, how do we apply it? What are the applications? They are best suited for the food products which have low electrical conductivity, and so that breakdown should not be there of the product. And further, if you see that products, it should be suitable that it can be taken through that channel, whatever channel, whether it is a tubular or a channel mode or some other design. So it should be able to flow with. However, the solid material can also be exposed for the different purposes. But primarily, if you are targeting for preservation or the processing purpose, it is mainly suitable for the liquid kind of product or the beverage kind of products. However, it can be taken as a pre-treatment for the solid material also, like fish or other solid foods. There are different applications which are shown in this figure. Like it says that extraction, cold extraction, or if cutting or like drying, or the osmotic treatment. If there are plant products which are exposed or the slices in the form of slice or in the whole form or the large size, what will happen? The cell will be influenced. So cellular breakdown would be there. Say for example, extraction is the interest, then there would be more access to the bioactives which are otherwise not available for the normal extraction conditions. The water which is otherwise difficult to remove for the drying is now exposed due to the cell rupture, and it will help in drying of the products. So it is as a pre-treatment can also be applied. There are different applications. Processing, if we talk, it mainly inactivation of microbes. and with the preservation of taste, sensory values, and so on. So that is how the applications are there, which are multifaceted. Now, looking into how does it influence the quality and the safety in the food? Is it safe to consume a product which is PEF treated or not? Here, like in thermal processing, what do we consider? We consider temperature, we consider the process time. They are two important aspects other than the sensitivity of product with heat. So in this particular thing, there are variables which could be included: field strength, duration, number, electric pulses. Means there is pulse. How many number of pulse? So pulse is there, which is of for a certain time. Pulse width in unit of the time multiplied with the number of pulses to be given, and so that will account total process efficacy. What extent of processing we have done, and sensory quality, which is much better than the conventionally processed food. They are heat sensitive, nutrients are better preserved, like vitamin C, flavors are better retained, vegetative bacterial cell, it can very well inactivate, yeast are also sensitive. And but if you see that spores, yes, certainly it is not a sterilization kind of method. And PEF, if you see that it is effective against the listed microorganisms, if you see E. coli, which is considered to be a pathogen, B. cereus, lactase, L. lactase, Pseudomonas. So their efficacy is there. Certain log reductions which have been reported even up to the 4 CFU reduction can be easily attained, 3 to 4 kind of log reduction. It is not only the that microbes, but also can influence the enzymes, but it reduces enzyme activity, but depends what enzyme we are targeting for. Like there are PPO, polyphenol oxidase, is very well known for the blanching purposes, you would have studied, and they are threat to the browning of fruits and vegetable. So they are resistant one. But if you see the other side, there are a few which could be easily to for inactivation: protease, papain, lipase, amylase. They can be inactivated, but with high electric field intensity. So that's the limitation. Now we'll see some details of the some similar technologies, but it is not the electric field based. It is the pulses of the light which we are exposing. So ultimately, it's a kind of radiation or electromagnetic radiation. So, and in this, the pulse is given of light, and we have just studied, or means I just explained the pulses where electric field pulses we were giving. So here in this technology, we inactivate microbes. Particularly, it is effective on the surface microflora inactivation, or it could also be applied to the liquid foods or the food, some of the food packaging materials. What does pulse light mean? It is a high power electric current if we pass through an inert gas, and in that what happens that it converts that current to the high power light pulses. The pulse light, it consists of high intensity light pulses, and basically the broad spectrum and the wavelength range is 200 to 1100 nanometer. And important also is here that very short duration, it is just not more than 2 milliseconds. And in pulse light, what we are attempting the inactivation of microbes, and the effect which they generate, they are combination of photochemical and photothermal effect. In terms of application, if we see that pulse light can be applied for the liquid food mainly, like milk, juice, water, meat, and fish. Here only the surface inactivation can be targeted. Minimally processed fruits and vegetable could also be an area of application. Packaged food products like wheat flour, corn meal is another example for application. Effectively, they could be also used for surface contamination of the packaging material. And key component in the pulse light is that flash lamp, which is filled, that I already explained. And like inert gas, if we have xenon, and it can generate and emit the radiation, and radiation will be prominently dominating to what? Dominating with the UV. So that's how the disinfection is quite good. Now, for another method of or the technology in the novel technologies, that is ultrasound application for the food. Ultrasound, it is definitely a sound wave, and it is an advanced, safe, non-thermal green technology. Basically, ultrasound refers to the frequency range, which is 20 to the 100 kilohertz frequency, and here there further it is classified at that power ultrasound or low intensity ultrasound. Low intensity ultrasound, which is range between 2 to 10 megahertz. Here, it is important that in terms of the application, there is a difference. If we have, say, for example, ultrasound, which is propagating in a liquid medium and series of compression, rarefication, it will give, and that too, if it is a power ultrasound, it will cause, and so like if it's rarefication compression, it goes like this, so causing a cavitation, means bubbles which are formed, and they could be collapsed, and that will lead to the high thermal effect or the mechanical effect in terms of the pressure, and thermal effect in terms of the very high, very localized kind of temperature. It's not that overall temperature is being increased, but release of energy instantaneous at a particular point, so that leads to the inactivation of the microbes, and the chemical effects, of course some free radicals formation could be there. If you want to visualize the movement and how does it work, how the cavitation, that can be seen in this figure. And high pressure and temperature together will lead to the molecular fragmentation, cell rupture, and the inactivation of microorganism or the cells will take place in this process. But now coming to the application of ultrasound, ultrasound again has a multifaceted application. If we target that inactivation for the preservation, that is one aspect where if you take the low intensity ultrasound, they can be used for the imaging purpose and non-destructive testing of food, they can be applied. Power ultrasound mainly for the food processing in terms of the microbial inactivation, 2 to 3 kind of CFU load reduction. Other applications, because they can create a good emulsion. So high homogenization emulsion based products can be given up. This could be means ultrasound can act as a processing aid, and filtration of the production of the fruit extracts, drinks, brining of the meat cheeses, and tenderization of the meat product, drying of the heat sensitive food, and so on. These are the applications which can be there. Ultrasound can also be applied and as an aid for the freezing, crystallization, so that freezing can be made faster. That is what they can also work for. In the list of moving further for the novel technologies, we will now start the discussion on the supercritical fluid technology. So here, what is first to see that what is the state of putting a fluid in a supercritical stage. Here, particularly in terms of, if you see that temperature and the pressure. So there are certain temperature and pressure with reference to a particular fluid. They can be named as the critical temperature or the critical pressure. And if we are able to bring that fluid up to that, so there is a zone you can get particularly after critical point. So superheated vapor or superheated fluid. This particularly going beyond that critical temperature, if you see that particular figure, after crossing this limit of critical pressure and critical temperature, here this fluid can exert altogether different properties. So their chemical, physical properties are in between the liquid and gas, and thereby they can be very good solvent. They can be applied for the extraction purposes. For the food applications, CO2 is mainly used as a fluid. And why it is popular as a supercritical fluid? Because it is non-toxic, odorless, so interaction with the food goes very well. However, water, ethanol, and other fluids can also be used, but most popular, most suitable is CO2, which is considered, and they are applied for the extraction of the valued compound, which are very small amount present in a particular material or waste or the food material, but their extraction can be here very easy, and this is treated as a green technology. Now coming to another technology, that is plasma technology, application of the plasma. What is plasma? Plasma is an ionized gas which can consist of free electrons, ions, reactive atoms, or neutral molecules and photons. How does it produced? If we have a material which is either in the solid liquid state or the gas, means if we put energy, gradually there is a change in the state. And after gas state, if the further it is very high energy is transmitted, then it can convert into the, or it can come to the state of the plasma. And in plasma processes, particularly, you see that there are charges, there are, you can say that neutral molecules, photons, and ions, but net charge is zero. And among different plasmas, there is one type of plasma which is atmospheric pressure plasma, and also almost at the near room temperature plasma, that is called the cold plasma. This plasma has recently got good application in the food, particularly in terms of disinfection, and that too in the surface disinfection. So it works well for the vegetable, fruits, as a minimal processing, or on the packaging surfaces. So this application is called the cold plasma application for the food processing. This is one of the novel technologies, and it can be targeted for extension of the shelf life. The example here in this figure, you can see that say tomato, on the surface you have treated, so it will not, the fungus which is available on this particular surface, it is inactivated, and if it is treated, during the storage or the study period, it has not grown up. So that's how the food can be preserved. Application, particularly in terms of the plasma, surface decontamination would be very important to cite, and other than this, the toxin, pesticides, they can also be inactivated. Some printing applications, modification on the packaging surface can also be done using plasma. Treatment of the wastewater has also been tried, and effect in terms of food safety and quality, it is mainly disinfection. So it could act as the minimal processing kind of application, being a non-thermal application, and it almost give no effect on the nutritional properties or the sensory properties of the food. It can also inactivate enzymes like trypsin. So that is how the cold plasma is applied to the food. Now we will study the details about the irradiation of the food. We have already seen the exposure of food to the other electromagnetic wave, or means electromagnetic radiations. But now we will talk irradiation, and particularly irradiation means ionizing radiation we are referring here. So what is this ionizing radiation? If we put the food material, or we give the food material an exposure of radiation in this whole electromagnetic radiation, particularly spectrum, if you see, then, but some of the high energy radiations, what they are able to do, if short wavelength, it means h nu or hc upon lambda. If so wavelength is less, then for a short wavelength you will get a high energy impact, and they will cause the liberation of the electron molecules, or the atoms will be excited. So that is how the ionization can be caused, and that ionization effect in the food systems, that may lead to the inactivation of microbes, and even up to the level of sterilization, not only limited to the pasteurization. How? It is particularly because it may cause permanent damage to the DNA of the microbes. So that's how the microbes are inactivated. Looking to the sources of ionizing radiations, there are some permitted sources which I would be mentioning here for the food applications. Cobalt-60 is one of the important isotope out of the other radioactive isotopes. There could be cesium, selenium, but cobalt-60 is prominently used for this purpose. And X-rays are also permitted, but here the energy should be less than equal to the 5 mega electron volt, and electron accelerators where the energy level would not have crossed 10 mega electron volt. So these are the sources used for what kind of applications? If we look for the applications, number one, there is a regulatory requirement. If we see in the country, we have the sign of the Radura, which FSSAI has permitted that radiation can also be used, but you have to declare food is irradiated. FSSAI is the regulatory authority of the foods in the country. And what kind of applications it gives? It gives mainly the applications which are taken. They could be the delay in the ripening, delay in the sprouting. There could be disinfective applications in the herbs. There could be also in applications which are commercially, some of the exports like mango. If we want to export, it is essentially that has to be irradiated, then only can be exported as per the conditions of some of the European and US in particular. Looking for another method of under the novel technologies, that is using ozone for food preservation. That is called the ozonization. So ozonization is because ozone is a gas. So it's a chemical disinfectant which can disinfect, or you can say that reduce the microbial load on the food surfaces, or within the food, or even the you can say the utensils it can disinfect. How does it work? Generally UV radiation or the corona discharge, which can be used for the production of ozone. So if the ozone is available and being highly reactive and unstable, they are advantage. So highly reactive, it is inactivating microbes because it is damaging cell envelope, or the leakage of the cellular material it may cause, oxidation of the cellular protein for the reactivity point of view. And another thing is that its residue is not there because it is unstable. So that's an advantage, and that's how this novel technologies is considered eco-friendly technologies and good for food, and particularly where as a substitute of chlorine. Applications are mainly for the water, beverages, fruit and vegetables for the washing purposes, herbs and spices. Disinfection can also be taken through this application of ozonization. A figure is showing that how, if the ozone is there, oxygen is there, ozone generator, it converts it to the ozone, food is exposed, and then it is again disintegrated, and only O2 is released and food is disinfected. On the same line, there is another technologies using ultraviolet light exposure to the food and for the purpose of disinfection. And in this UV light, which is a non-ionizing radiation, and the range of wavelength, if we see that 100 to 400 nanometer, that can be applied. And within this wavelength range, there could be UV type A, type B, type C. And out of this, particularly UVC is prominently germicidal or disinfective, microbicidal. That is applied to the food because it damages the DNA of the microbes, and there how it inhibits their growth. So this is that's how it is applied for shelf life extension of the food material. It can be produced in the UV light. We can have the UV lamps directly giving this exposure to the food. And application could be, for example, if there is a line, you can have the fresh commodity moving through that line. On the top of it, you can expose it with the UV light. Some the liquid food processing can be done. Even in some of the packaging sections, the atmosphere can also be disinfected. Surface disinfection could be there where food material is to be placed. So these are the applications which are there for the UV radiation. Now coming to, so far what we discussed are non-thermal novel technologies. There's one example I'll take of thermal example, which would be the thermal technology, but as a novel technologies. It is not using a conventional way of heating. That is ohmic heating. It is a novel thermal processing technologies. In this, what is we are targeting? We are targeting heating. We are increasing temperature, but it is a electro heating, electrical resistance heating, or the joule heating, it can also be termed, where the normal 50 to 60 hertz frequency can be used, and you have the food material and you are passing that current through it. The principle, it works on the ohmic law or the Ohm's law, where electrical energy is being dissipated into the heat because food is offering certain resistivity. So it will depend at what resistivity it offers. Though it is a food for which insulating type of food, it cannot be applied. Like if it is fat, It is not good for that. But if food is conductor but with certain resistivity, then heat can be generated. But important is this is rapid and uniform. So rapid and uniform advantage in terms of better sensory quality, better nutritional quality, and that is how it is applied for the food applications. We are blanching, cooking applications, baking applications, sterilizations, or some aseptic heating if we want for aseptic processing, thawing, evaporation. So there could be different processes where the heating is required. You can also rely this as a novel method, novel approach, and an alternate to the conventional heating. It can also be used for the milk, meat, example, if the fruits and vegetable, egg, liquid of the egg, and mainly for high viscous where it is difficult to otherwise handle. You can more uniformly, more rapidly can heat those products, soup, stews, syrups, or the sauces. And the heating during the ohmic heating is very rapid and homogeneous. That's an advantage. For that purpose, it is being used nowadays as an alternative, and it is ultimately giving an effect of retaining better quality, better color, better aroma, and better sensory appeal. So this is what we discussed today. The alternative method, they are alternative to the thermal process. That's how they are called the novel processing technologies. And I will request the learners that they can refresh it. I'll have certain questions like what are the principles on which the high pressure works. Just try to recall. If you are not able to recall, please rewind and see it again. On what principle we have just studied that ohmic heating works. Now, like what is the unit of radiation? I mentioned that radiation of the unit is gray, or sometimes it can be mentioned in the kilogray. What are the applications of the radiations? What are the limitation of the radiations? So those all things you can learn well through this particular lecture, I hope. Thank you. All the best.